Hello! Welcome to Teach Me Maths. My name is Jonathan Hicks and we're doing t-tests. Now this is the unpaired or independent t-test. I've done an overview video which explains the difference between the different kinds of t-tests, but this one we're taking data that's not paired. So go and watch the paired t-test video if you want to know about that, but in this one I'm just going to give you an example of how you calculate the t-statistic or t-value and then use that to draw conclusions about your data. Remember, for a t-test we're comparing the means of two samples. We want to know if the mean is maybe higher or lower or just different in some way, but that's the kind of situation we've got. Alright, so for this one the example I've chosen is leaves. We're measuring the length of leaves. So imagine you've got two bushes of different varieties of plant and you measure the lengths of 30 leaves off one bush and then 30 leaves off a different bush, which look quite same. They're both quite bushy, but you're just wondering maybe the length of the leaves on one bush is longer than the others. And then you record the results, you work out the mean, and then we can compare the means to see not only are they different, but if we can make a general statement about this particular variety of bush and whether or not the length of the leaves are always going to be different, longer or shorter, than the length of the leaves on the other bush. Right, so before we launch into that though, when we look at the data, we need to specify our hypotheses. So you have the null hypothesis and the alternative hypothesis. So the alternative hypothesis, if you remember, we're saying that there's no change, no difference. What we're hoping to see, so in this case that the length of the leaves is different on one plant than the other, the H0 though says that there's no difference. So in this case there's no difference between the lengths of the leaves. H1, the alternative hypothesis though, says yes, there's a difference. Now crucially here, we don't know which way that difference is going to be. So there's a difference in leaf length, but we don't know whether our first variety of plant has longer leaves or if our second variety of plant has longer leaves. We're just going to compare the two sets of data and see if there is a difference. So H1 is there's a difference. When it comes to looking at the t-table and things, this is going to be what's called a two-tailed test because we're looking for a difference in either direction. We're not just expecting the leaves to be longer. They could be longer or they could be shorter. So that's what you call a two-tailed test, and the name will make a bit more sense when we actually draw the distribution. You'll see the picture. You'll see, that's why it's two-tailed. So those are our hypotheses: null hypothesis, alternative hypothesis. Let's look at some data. So here we go. These are the lengths of 30 leaves from the two varieties of plants. We've measured these in millimeters. Now the key difference between paired and unpaired tests is that on a paired test you'd be working out the differences between them, whereas on an unpaired test, which is what we've got here, you'll just have to work out the means and the standard deviations, etc., of the two samples separately, and then we'll combine them to get our t-statistic or t-value in a minute. But the important point to notice here, the reason why this is unpaired, is there's no natural way to pair the leaves from one plant with the other plant. You've just taken 30 leaves off one plant and 30 leaves off a different plant. They're not dependent on each other. The length of one leaf is not going to correspond with the length of a different leaf on the other plant. It's just two sets of data, and they might even be different sizes. In this case, as it happens, they both have 30 points, 30 data points. So there's 30 leaves from one bush, as I say, and we're taking 30 leaves from the other one. But they could be different. It might be 28 and 31 or something like that. It's important that they're not too different. They must be roughly the same. You can't have 30 leaves from one plant and 60 leaves from the other plant. That would not be good. But as long as they're about the same, it's fine. All right, so that's the data. And essentially we're going to calculate the t-statistic based on that data. Now let me write down how you work out the t-statistic and then we'll try calculating it. Okay, now this is quite a big formula. It's a lot more complicated than the one for the paired data. Okay, so bear with me, I'll explain what all the bits are. So the t-value that you're going to be working out and then comparing with the table in a bit is a giant fraction, first of all. On the top of this fraction you've got x1 bar minus x2 bar. Now x bar is the mean, remember, so x1 bar is the mean of the lengths of the leaves in the first sample, and x2 bar is the mean from the second sample. So that's fairly straightforward so far. On the bottom of this fraction though, you've got a giant square root. Everything inside here is going to be square rooted in a bit. And that's made of two brackets, we'll say. This bracket is another fraction. So here you've got n1 minus 1. So that's the number of samples in your first group minus 1. And you times that by the standard deviation of that group squared. And then you add to that the number of samples, the number of leaves in the second group minus 1, and times that by the standard deviation of the second group squared again. So these two things are exactly the same, but for the two different groups, and then we add them together. On the bottom of this fraction is actually going to be the degrees of freedom. We'll talk about that in a bit, but it's n1 minus 1 plus n2 minus 1. Yeah, so the number of samples from the first group minus 1 plus the number of samples from the second group minus 1. And then over here you have 1 over n1 plus 1 over n2. Now that is a beast of an equation, and I don't remember this one, I have to say. When I need to work this out, I just look it up in a formula book or something, and then you can stick all the numbers in and work it out. So you won't be expected to remember this. If you need to do this for an exam or something, they'll give you this in the formula book, I'm sure. So just to remind you then, we've only really got three things to work out here for the two different groups. So you've got the number of samples, the mean, and the standard deviation from group 1. And then you've got the number of samples, the mean, and the standard deviation from group 2. So two different groups, you work out those things, shove all those numbers into this massive formula, heat equals on the calculator, and out pops the answer, in theory. Now I'm not going to go into all the details of how you work this out, okay? Suffice it to say, when you compare the two sets of data, if I give you the values here, the mean from our first set of leaves turns out to be 24.21. The standard deviation from the first set of leaves is 1.48, and the number of leaves in that first sample is 30. I mean, there are 30 leaves in both samples. But for x2 bar, we've got 16.91. S2, the standard deviation from the second group, is 1.81, and the number of samples in the second group is 30 again. So those are the values when you work them out. Again, I'm not going to go into the details of how you work out mean and standard deviation. I'm assuming you're happy with that already. So you shove all those numbers into here on your calculator and work it out. Now again, I'm just going to give you the answer in a minute here, but just by way of a tip, the way I would work this out if I had to do it personally on a calculator right now, I'm not going to do it because it's just too time consuming. I would work out the top of this fraction, see what I get, work out the bottom of the fraction, and then divide those two things. So I'm going to get one number from that fraction. I'd then work out this bracket, which gives me another number, and then I'd multiply those two numbers together. Then you take the square root of that, whatever that whole thing turns out to be. Be very careful not to forget the square root here, very important. Once you've got that big square root number, work out the top of the fraction, divide it by the previous answer, the big square root, and that gives you your t value, or t statistic. And in this case, after much calculating, it turns out to be 17.1. Ta-da! Right, what does that mean? Well, as I said from the overview video, the point is here that the t value measures how much of a difference there is between the samples, and it takes into account the variation or the standard deviation. So the bigger the t value, the more reliable difference there is between the two samples. And I can tell you now, t value of over 17 is huge. Anything over 3 is pretty big. 17 is really big. So that means our data, the two sets of leaf lengths from your two bushes, are very different. The leaves on one bush are significantly different from the leaves on the other bush. We don't know which direction, which one is longer at the moment. We just know that we've got a big t-value, so that's a big difference. So how do we draw a conclusion? How do we compare that with our hypotheses here? And with what confidence can we say that there is a difference between the leaf length? Well, in order to do that, I'm going to try and draw a t-distribution for you and explain why it's two-tailed and how we draw conclusions using this value of 17.1. So I'm going to get rid of that lot in a second. So let me stick the t-value here. T equals 17.1. We're going to need that. Let me get rid of all this so I can draw you a nice picture. Alright, so a t-value looks like a normal distribution, kind of. It's a bit fatter at the sides. Something like that. And we're expecting there to be a difference, which might be that the leaves on one group are longer, or they might be shorter. Yeah, we might be going one way or the other, we don't know which way. So that's what makes it a two-tailed test, because we're looking for a critical value. We've been matching these two values here, but it could be in either direction. Now, as I say, typically, in order to reject your null hypothesis and to accept that yes, there is a difference between the lengths of the leaves of the two bushes, you generally want to be at least 95% confident. So you want 95% here, which means you need 5% in the two extremes, the two tails. These are the tail, that's why it's called a two-tailed test. But if you're splitting 5% equally between these two halves, then that means you're going to have 2.5% here and 2.5% over here. So you then look up in your t-table the values. Now at this point you've got a choice. Some t-tables will give you results for one-tailed and two-tailed tests. Now we want to be 95% confident, so we want 5% here. So you can either look up a two-tailed test at the 5% level, or if you just forget about this for a moment, that bottom half, and just look at the top half, the value here is actually the same as doing a one-tailed test at the 2.5% level. So it doesn't actually matter. And if you've got a t-table which doesn't even have a two-tailed line, which you might not do, you don't need it really. Just take whatever your one-tailed thing is and use half the value. So if it's a 5% level, halve that to get 2.5 and do a one-tailed test. Either way is the same, because the value here is going to be the same. Yep, 2.5% on the right, that's the value you're going to get from the table. So let's have a look at the table. There we go. So degrees of freedom, they're down the left-hand side, and along the top is the probabilities. Now, as I say, we're wanting a 95% confidence. It's a two-tailed test, so if we go along, we're going to find the 0.95 level. And if you look along the one-tailed test, you see that's the same as the 0.975 level. Or equivalently, if you're going the other way, 95% is going to be 0.05, or if it's half of that for the one-tailed, it'd be 0.025. But either way, you find the 95% level for the two-tailed test, let's say. And then you read down until you get to the degrees of freedom along the left-hand side. Now the degrees of freedom are the number of points, if you remember, it was n1 minus 1 plus n2 minus 1. Yeah, this is the degrees of freedom. So when you work this out, we have 30 points in each. So 30 minus 1 is 29. And another 30 minus 1 is another 29. Add them together, you're going to get 58. Now, looking at our t-table down the left-hand side, we don't have a 58. We've got a 40 and we've got a 60, but no 58. What are we going to do? Well, what we can do is just take the two values either side and then hope to make a conclusion. If we end up sitting between those two values, our t-value here, we might have an issue. But with such a big t-value, we will be fine. So if we read off the values, you can see that at the 95% level, for the two-tailed test, if you go down to 40, you're going to get, like the 40 and the 60 ones, you're going to get between 2.000 and 2.021. Yeah. So if we go back to our picture, the value here, the 2.5% level on the one-tailed test if you like, or you can take them both into account, the 5% level on the two-tailed test, this point here is somewhere between 2.000 and 2.021. These are the values for the 40 degrees of freedom and the 60 degrees of freedom from our test. And we had 58 degrees of freedom, so we know that the critical value is going to be somewhere between these two. We don't know exactly where. But our t-value, 17.1, was bigger than both of them, by a lot. So that's great. We know that at the 95% level, because our t-value is bigger than the critical value, which we don't know exactly what it is, but it's somewhere in this range, we know we can say with 95% confidence that there is a difference in the leaf length. Now, it'd be nice to say even more confident, particularly as we've got such a big t-value, we might be able to be even more confident. So if we go back to our table again, maybe we can look at the 99% confidence level. Now again, if we look at the two-tailed test, the 99%, 0.99, and we go down to 58. Now again, we don't have the 58, so between 40 and 60, we're going to get two values. So you've got 2.600 and 2.704. Those are the two values. So if we go back to our picture, if I change this slightly now, so if we say that there's actually 99% here for our two-tailed test, that means you're going to have 1% remaining on the two extremes. So that's going to be 0.5% on each side. So you're going to have 0.5% here, 0.5% here, and the two for 40 and 60, the degrees of freedom we had in the table, the critical value at the 99% level for a two-tailed test was, as I say, between 2.660, I think it was, and 2.704. All right. So again, we compare our t-value, 17.1, with the critical value. And again, we don't know exactly what the critical value was. It's between these two, but our t-value is much bigger than both of them. So there is definitely a difference. And we can say with 99% confidence that there is a difference between the leaf lengths of these bushes. The point here is that the chances of picking, obviously when you have a bush and it grows leaves, some of the leaves are longer than others. And it might be that you just were unlucky and that you happen to pick all the short leaves off one bush and you happen to pick all the long leaves off the other bush. So what would be the probability of just being unlucky, of actually having the same length leaves on average on both bushes, but just happening to pick out short ones and long ones? Well, our t value, the 17.1, is more than the critical value for the 99% level. So we can say there is a 1%, yeah, it's this one and this one, because we don't know whether or not they're longer or shorter at the moment. There's only a 1% probability of that happening by chance, of getting such a difference by unluckily, if you like, picking short leaves off one and long leaves off the other, or whatever it is. So you can be very confident here. And I mean, as you can see, with such a big t-value, you could probably go to the 99.9% level and it would still be bigger than the critical value. So you can decide what level. I mean, usually 99% is enough. 95% is generally considered enough, but if you can be 99% confident, that's even better. And we would reject the null hypothesis and say, yes, there's definitely a difference in the length of the leaves on these two bushes. Now, I talked about trying to figure out which way. We know there's a difference. There's definitely a big difference. 17.1 is a big number. But which way is it? Which bush has the longer leaves? Now, the easiest way to compare this is just to look at the means for the two bushes. So just to remind you, the mean length of leaves from the first bush was 24.21. and the mean length of leaves from the second bush was 16.91. So hopefully you can see, bush 1 had longer leaves on average than bush 2. And we can be 99% confident, because of how big our t-value is, that there is definitely a difference in the leaf length between these two varieties of bush. And so we could say with confidence that variety 1 has longer leaves than variety 2. Wasn't that worth it? Alright, so that's how you calculate the t-statistic. The formula is a bit of a nightmare, but you just calculate, as I say, the number of samples, the mean and standard deviation for each group, shove all the numbers in, out comes your t-statistic, and then compare it with the table. Just be careful about whether you've got one-tailed or two-tailed tests, and calculate your degrees of freedom like this, and then it all should be fine. Now, as I said in the overview, I've done another video on one-sample tests. So we've got the paired test, which I did in the other video. This video has been unpaired data, and then the last one is going to be the one-sample tests. So go and watch that one if you want to know about that. My name is Jonathan Hicks, and you're watching Teach Me Maths.